So this limiters, the advantage is that it's relatively simple to implement. As we can see that it involves a small subroutine, computing two, in the 1D case, computing two quantities called U delta and U double delta, modifying them by a simple formula and feed it back to build a new polynomial. And from a theoretical point of view, it does guarantee that the resulting scheme, at least when you use second and third order TVD, it doesn't have to be second, third order. As long as you use the TVD, longitudinal time discretization, which is sometimes also called SSP, time discretization, same thing. If I use one of them, then you have the final scheme is total variation diminishing in the means, our total variation bounded in the means. So there's a theory behind this. That's the good part. Bad part here is that for TVD, you still have some loss of accuracy. For TVB, you have unfortunately a parameter M, which you have to choose. So there are some bad parts here. Another limiter I want to briefly mention is a Weno type limiter. Weno stands for weighted essentially non-oscillatory. Weighted essentially non-oscillatory limiter. So Weno actually is not a DG technique. It is actually a technique for finite volume or finite difference schemes. However, it can be used as a limiter here. And most recent work in this direction, the JCP paper by Zhong and myself. I don't know, either, or it could even be 2013. Very recent paper. And this paper contains a rather simple, well, everything is complicated, but comparatively speaking, among all the Weno limiters, a rather simple strategy, which I will not go into the depths to describe, but roughly speaking, this is how it works. So let's say if you have the polynomials here, of course you don't have this bad kind of things, but this is the cell ij plus 1, ij minus 1.
Smiley face.
Smiley face. So suppose you have three polynomials in these three cells, and suppose for some trouble cell indicator you said this is a troubled cell. But you want to modify this polynomial. What do? Well, this is how the limiter works. So you have a polynomial P0, P1, and P2. All three of them are, let's say, third order polynomials. You first extend this polynomial. Polynomials, you can read it anywhere, right? You extend this polynomial to this cell, still call it P0. You extend this polynomial to this cell, still call it P2. And you have the original polynomial, which is P1. So you have three polynomials in this cell. All three of them are actually accurate because, right, they come from the original solution. It's a little bit like extrapolation. You extend the polynomial to your neighbor cell. It's still accurate if it's in smooth region. But of course, if in this kind of situation, then these two guys are much better than this guy. So maybe you can use a little bit more of these two guys, a little bit less of the other one. So the idea of a Weno limiter is to form the new polynomial Px, which is a linear combination of the three of them. Convex combination of the three of them. P0, P1, and P2. So this omega 0, omega 1, omega 2 are positive or non-negative numbers whose sum is 1. And there is a recipe to construct these three numbers, which is called a Weno procedure. So depending on the smoothness of these polynomials, there's a systematic way of constructing these coefficients so that smooth regions maybe you favor the middle guy more, but in short regions maybe you favor whoever is the less oscillator. So this, roughly speaking, this, but there's some small technical complication because the extended polynomial may not have the same cell average as this bad guy, but we said that any limit you can never touch average, right? Cell average is key. So you actually, in the practical thing, you actually shift this guy a little bit, you shift this guy a little bit, so that the polynomial has the same average as the original one. So you extend, you shift, then you get the same average. Then you do this average, and you do this Wiener business. This shifting doesn't affect accuracy either, because all three polynomials are accurate, right? So all three cell averages, even though they are not equal, they are all high order approximations to the same exact cell average. So you adjust them within that bound, it's fine.
You're shifting just the extended portion of the graph.
The extended portion. You only use the extended portion. You don't use it. Okay, so this limiter turns out to be workable. Working. You can see this paper. It's a JCP paper of Zhong and Xu, and there's a follow-up paper also for triangles. You can see this type of limiters, the best advantage would be an unstructured mesh, because unstructured mesh, this uses only neighbors. It doesn't use neighbors, and so on. So this is another choice. Of course, there are many other choices. As I said, this is an area which is underdeveloped. Well, you can say overdeveloped because there are many papers, but underdeveloped because there's nothing which can persuade everybody else to use yours. So I don't even try because I know these are not the optimal ones. So I only point out what is the advantage, disadvantage of each one of them.
You have a similar thing with finite volume difference.
Well, you see, finite volume, then this guy is very good, in my view, because finite volume, you have cell averages, and you reconstruct a polynomial in this cell. In this reconstruction, you can do many things. One thing you could do is this Eno and Wiener business. You can reconstruct a non-oscillatory polynomial. This DG, there's a polynomial there which you upgrade from time level n to time level n plus 1 already. It's very rigid. There's no place, well, there's a flux. You can throw in some different things in choosing different flux. But that's very little. Other than the flux, the DG has no freedom, right? Once the flux is fixed, the DG method is fixed. So where do I put the non-oscillatory fix in? There's no place I can stick it in. So that is why it has to be done in a predicted correct way. In other words, I use DG to compute. I get a polynomial, and then I change it. So this is why it's less natural than finite volume. Because finite volume, this Wiener is an integral part of the whole algorithm. So from this point of view, DG is less friendly to tricks for fixing oscillations than finite volume. Much less natural, right?
But this is for only strong shock cases, or
only for strong shock cases. Yeah. For example, he wants to compute very strong shock cases. Strong shock. Okay, so I will only say this much about the limiter, but will leave you with the impression that if you want to work, this is an active research area. So in DG, there are several active research areas. This definitely is one of them. So the other thing I mentioned towards the end of the previous part was that this proof of convergence and error estimates for non-smooth solutions, right? I proved it for smooth solutions. Non-smooth, so non-linear, non-smooth. It's very tough. So again, if you want to challenge yourself, you want to challenge yourself, then there are many. So sometimes people ask me, "Oh, it's all done. What can I do?" There's no talking to one another. That's never possible. many problems to work out. And also many challenging problems. Okay, so this is the limiters, and finally I would want to say, I think I would rather spend time with hyperbolic than jump into parabolic immediately. I would want to mention one last thing. This is because a lot of people mentioned to me about this Parsons principle positivity concerning this. One thing, this is new, right? Relatively new. It's only about a couple of years old. The other thing is that it really works very well. So I want to find this. You can put it into this category. So it is bound preserving means that, for example, if your PDE has a Maxwell principle, then it maintains the Maxwell principle. If your PDE has a positive density, positive pressure, then it tries to maintain numerically positive density, positive pressure. It maintains the bond that the physical system PDE has. Okay. So this limiter is somewhat related to this type of limiters, but this is much milder, much simpler, much milder, and that's the job. For example, bound preserving can be achieved by this guy. What I described by the min mod TDD, it can achieve the bound preserving because TDD is actually stronger than bound preserving. However, this I already mentioned that you will lose accuracy. It is a very strong thing. So sometimes you don't want to touch the solution that much. Is it possible to find a limiter which is A, very simple to implement, B, does not kill accuracy, and C, guarantees that the bound is preserved? So let me explain to you, again using DG framework, what this limiter looks like. Okay, let's go this way. Okay, so let me write down the DG scheme. A and V, right? EX. Hold on forward. So let's see. If I move it to the other side, it is what is it? It's minus. I think it's plus. Correct me if I'm wrong. I think on the other side it was minus, right? So this side is plus. Plus 2 boundary terms. This is delta t, sorry. Because this minus this divided by delta t approximates ut. So this is delta t. Then you have f hat j plus half. V of j plus half minus. This is at time level n. Plus delta t f hat j minus half n v of j minus half plus. So this is the scheme, DG scheme, when you discretize in time by Euler forward. This is true for every test function v in VH. So I just rewrite the scheme here. Now, when I talk about the cell average, I take the test function v to be 1 inside ij 0 everywhere else. Take this certainly is finite element space, right? It's P0 is already. So every Pk contains this guy. So you can take V to be 1. If you take V to be 1 and also you divide both sides by 1 over delta x, then this term becomes the integral of this polynomial dx divided by the cell length. So that's the cell average. This is the cell average. We're going to take 1 here divided by 1 over delta x. This one is also the cell average, but that time level n. And these two guys, this one disappears because it is 1 sub x, nothing. And these two guys, minus delta t. Remember, I have to divide it by delta x. I call this lambda. Lambda is delta t over delta x, the CML number. And times, this is 1, so you just get this. F hat j plus half n minus f hat j minus half n. Of course, this formula is familiar to you. It is so you can see that the DG scheme for evolving cell averages is identical to a finite volume scheme. The only difference is that this guy f hat n j plus half, which is f hat u of j plus half minus and u of j plus half plus. These two guys. These are, so this is the picture. You have a polynomial here in cell ij who has a cell average and also has this value at j plus half. So this value is u of j plus half minus. You have a neighboring cell, and then this point is u of j plus half plus. Now these two values for finite volume comes from a reconstructed polynomial from the cell averages, but for DG, they just come from the solution itself because there's no reconstruction. The solution is already a polynomial. Just read the value. But in form, right, at least formally, the scheme is identical. So that is why you work out a limiter for one, you work out a limiter for the other. Okay, so the problem here is this is what I would, my wish list. Wish list is that if my numerical solution at time level n, let me write it this way. So this is my numerical solution. It's a piecewise polynomial at time level n. If this is between small m and the capital M for all x, then the same inequality holds for next time step, polynomial at the next time step. Why can I ask this? Because I'm solving a scalar conservation law. So remember, this time I'm solving this scalar nonlinear conservation law. This scalar conservation law, the entropy solution does have this property. Namely, the initial condition, if the initial condition is between small m and the capital M, then the entropy solution at all later time will be bounded between small m and capital M. So this condition is very reasonable because it is satisfied by the exact entropy solution. So I'm not asking something which is impossible, right? I'm asking something very reasonable. So this is my wish list. So let's see how we get this. Let's do this in several steps. The first step, so you do research, you always start from simple things, right? So you don't want to jump. So you do, what do you do? What? You first look at how do you prove such a thing for first orders. If you cannot even do that, then you're going to want to highlight. So first order scheme, I can write it down. It is this. It's similar to that. The only difference is that here I put the cell average in directly. The two arguments are no longer j plus half minus j plus half plus. They are just the cell averages. So this is the first order scheme. This, let me denote this by a notation h lambda, which depends on three guys. U bar of nj minus 1, U bar of nj, and U bar of nj plus 1. It's just a notation. So you see the right-hand side depends on three numbers. U bar of nj, U bar of nj minus 1, and U bar of nj plus 1. So it's a function of these three guys. It also depends on the second number. Okay. So we know that f hat is such a function. So f hat is increasing in the first argument, decreasing in the second argument. Now, how about capital H lambda? Capital H lambda, I claim, is an increasing function of all three guys, provided lambda is sufficiently small. How do I know that? Well, just for example, let's do the easiest thing. Let's take partial derivative, assuming that these guys are all differentiable. It's easier to do it that way. So you take the partial derivative with respect to this first guy. What do you get? Well, it appears only here. So the partial derivative is minus minus, so it's a plus. And f with respect to the first argument. The partial derivative of f hat with respect to the first argument. But f hat with respect to the first argument is increasing. So that means this thing is positive. That means this thing about the first argument is increasing. About the second argument, it appears in 3 places, here, here, and here. So I just take the derivative, so it's 1 here. It appears here minus lambda f hat 1 plus lambda, so minus here f hat 2. I'm a little bit sloppy, right? What that means is that it is the derivative, partial derivative of this guy with respect to the first argument evaluated at this location. So this thing, well, these are of wrong signs because this is positive, there's a negative sign here. This is negative, so it's the negative is positive, again with a wrong sign. So this whole business is a wrong sign. It's a positive guy. So it's 1 minus a positive guy. So eventually it will become negative. However, there's a lambda here. So as long as these guys are bounded, if lambda is less than 1 over that bound, then I'm in business. So this thing is positive. So that is why you have this condition. And finally, partial h lambda, partial the third guy. Third guy appears only here. And it's a negative sign in front. So it's minus lambda f hat 2. But the f hat is a decreasing function of the second guy, so f hat 2 is negative. It's a negative, so it's positive. So you see, this is why the scheme is called monotone scheme, right? That's why the scheme is called monotone scheme for a reason. This is the reason. If you read all those 3 guys, there is an increasing function of all 3. I'd be happy. So it's all 3 of them. So if it is a monotonically increasing function of all 3 of them, then it is very easy to prove this Mason principle. So in other words, if all 3 of them, j minus 1, j, and j plus 1, all 3 of them are between capital small m and capital M, then u bar of n plus 1j equals to h lambda of u bar of nj minus 1, u bar of nj, u bar of nj plus 1. Since it is an increasing function, and since each one of them is less than capital M, if I replace each one of them by a bigger number, I will get a bigger number, no? Increasing function of all 3 guys. So, but this is what? This is when you take here to be capital M, capital M, capital M, capital M, capital M, but that is f hat capital M M. F hat capital M M will cancel, you just get capital M back. So if you put all 3 guys to be the same, you get M back. So u bar of n plus 1j will be less than or equal than capital M. By the same token, by the exactly the same token, this is bigger than small m. So Mason principle for first order scheme is proved in a trivial sense using monotonicity. So this is something I need to use. Now let me try to see how I can then do higher order schemes, which is here. I will be less lucky, much less lucky actually. So this higher order scheme, I will try to prove the higher order scheme. First of all, you might say, let me do this, let me do the following. Let me write this, which is by definition this thing. I will not write n because everybody on the right-hand side is at time level n. So make my notation a bit easier. It is this now, right? So if I try to do the same thing, g lambda, now this time it's not a function of 3 guys. It is not a function of 3 guys. It's a function of 5 guys. So it's u bar of j, this, 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 and this. Depends on 5 guys. Okay. Now, what would be a reasonable assumption? A very reasonable assumption is that all 5 guys are between small m and capital M. This is a very reasonable assumption. Why? Because, of course, the cell average should be between small m and capital M, but if the function is. And also, every point. So these guys are all point values, right? These guys are all point values of the polynomial at some n, so they should be between. So this is a very reasonable assumption. The question is, if I assume this, can I conclude that my U bar of n plus, forget about the points, just the cell average, can I conclude this over the other side? Is this true? With this assumption, with this scheme, with this being a monotone class, is this always true? This is a question you ask, right? You easily build a counterexample. No. You can pick 5 numbers which are all between 0 and 1. And this guy is above 1, no matter how small you pick a number. Unless you pick a number to be 0. If you pick a number to be non-zero, no matter how small, this goes out. See, the example is very easy to cook. Why is it very easy to cook? Because this G lambda, the answer is no. The problem is that this G lambda is not, if you want to mimic this proof, G lambda has to be an increasing function of everybody, but it is not. It is an increasing function of this guy, no problem, because it is here, 1. It is, how about this guy? This guy has a problem, because it's an increasing function here, but it's a negative sign. So, this the second guy is the troublemaker. The third guy is fine, because it's a decreasing function here, it's a negative sign. The third guy is fine. The fourth guy is again a troublemaker, because it's increasing. No, the fourth guy is fine. Sorry. The fourth guy is fine, because it's minus is positive, and f hat is increasing. And the last guy is the troublemaker. So there are 2 troublemakers here, so that the G lambda is no longer an increasing function of everybody. So you cannot mimic this proof. So that's the fundamental reason that you can easily build a counterexample. You just look at these wrong guys and you use them to build a counterexample. So these people basically at this stage people got lost. Basically what it says that by working with these 4 numbers, because this number you cannot change, that's our average. You remember, right? It's a sacred, either finite volume or DG. You never touch the cell average. So these 4 guys you can change, but I can only think of changing them so that they go into the bound, right? If you want to further change them, I have no guiding principle. How do I change them? So then if you further change them using some fancy, let's say TDB type min mod things, then okay, that kills the accuracy. But if otherwise, how do I change them? I know that if I don't change them, if I only require them to be in the bound, that's not enough. Counterexample immediately. So I need to change them, but I don't have a guiding principle. How? So that is why it stopped from people from getting good limiters, right? So they put too strong change. And then, yes, you achieved the bound preserving, but at the same time, you lost the accuracy. Okay, so how do we overcome this difficulty? Okay, so if you look at these 2 bad guys, there is something very interesting. Who are these 2 bad guys? This is the cell average, this is the polynomial. The 2 bad guys are these 2 values, namely u minus j plus half and u plus j minus half. These 2 guys are the bad guys, am I right? The second guy is u minus j plus half, and the last guy is u plus j minus half. So the 2 bad guys the polynomial, this is a polynomial, remember. This is a polynomial. It's the endpoint of this polynomial. These are the two bad guys. The G number doesn't depend on them in a nice way. However, it comes from this polynomial Px. This Px, the information of Px also appears in the right-hand side in U bar J. U bar J is the cell average of the same polynomial Px. And U bar J is a good guy. It's also very good, right? It's a real good guy because it has a 1 here. So it has a lot of weight. So it's like there's a good guy here with a lot of resource. And two bad guys, that poor guy, going the wrong way. So what's the way to do that? Well, good guy, come on, contribute a little bit to the problem. Just contribute a little bit, right? So contribute so that everybody is happy. So exactly the idea. That's the way I'm doing. So you just rewrite this thing, U bar J, as the two bad guys. Is it possible? At first you ask. Plus something else with positive weights. So what would this remind you? You want to write this is an integral. It's an integral of the polynomial as point values. Quadrature. So you open the quadrature book, you need to use the two endpoints. So these kind of quadratures are called Gauss-Labato quadrature. So you use a Gauss-Labato quadrature, which is exact for your polynomial degree. Let's say if your polynomial degree is 3, then Simpson is already good enough. If it's 4, maybe you need one more point. So you use a suitable Gauss-Labato point, then this thing becomes omega 0, omega capital, I don't know, capital K, K points, plus some middle guy, plus summation of L from 1 to K minus 1 of omega L, P of X, J, L, plus. Yeah. So this is a quadrature rule. It says that I'm using some middle points as well. So I'm using the two boundary points plus a middle point, quadrature points. And then I rewrite the integral of the polynomial as the quadrature sum. So there's a quadrature weights and the quadrature function value. The catch here, the real thing here, important thing here is that this is an equality. There's no approximation, so that's important. But I can do that because this is a polynomial. Polynomial, then I can use suitable Gauss-Labato so that there's no error. So this formula is exact. And all these omega L's are positive. This is, yeah, you know that you open the integration book. That this goes that. Okay, so this is what I meant. You borrow a little bit. You lend a little bit to the other guy. So now you have something that you can lend to the other guy, right? With positive weights of that. Okay. So now I'm in very good shape. So basically I can mimic so this is no good. However, I don't do it this way. I rewrite this as omega 0 u minus j u plus j minus half, right, plus omega k u minus j plus half plus the remaining sum. That's 1 to k minus 1 of omega L P of X JL. It's just notation. This JL are just the middle. There are some middle quadrature points. I just denote them by JL. So this sum takes care of this. Here, I simply put add and subtract. Let me see. What do I need to do? I would like to have j minus half here. want this. And also here, I would want this. Up to now, I just copied down what I have here. I replaced this by these three guys, I copied down this. But you probably can guess what I'm trying to do. I'm trying to add and subtract the term so that this part becomes the first order operator of three guys. So the first order operator, if you notice, the important thing is that this guy must be the same guy as this guy, must be the same guy as this guy. Right? So I have this guy here, which must be the same as the last guy, that's fine. It also has to be the same as the first guy here. So I copy down. Whatever is here, this is already the first order operator. Right? And by the same token, this guy has to be the same as this guy, which is okay, and also the same as, copy down here, and the same as this guy. So I copy down here, same thing. So then I know what it should be. And that's it. I'm okay. So I add and subtract. What I add and subtract, I have a clear purpose. I just want to make this part to be a first order operator acting on something. So this is, in my notation over there, is omega 0 times h lambda over omega 0. Because if I pull omega 0 out, I put a parenthesis outside, then I have to divide this by omega 0. So that is why it's a division by omega 0. So it's a first order operator with a modified CFL number of the three guys. Which three? Well, the first one is the guy here. Is the guy here. The second one is the guy here, which is the guy here. The third one is the guy here, which is here. Right? This guy, this whole caboodle, is equal to this. Right? My definition is just copy. Plus omega k capital H lambda over omega k of three guys. So again, the first guy is here. Is the second is u plus j minus half. The second guy is just here, u minus j plus half. The third guy is f hat of the second. So f hat of the second this plus the remaining. Good. Now I'm in business. Now let me assume that P, X, J, L, all these guys are between small m and capital M. In other words, the polynomial, when evaluated at all these Gauss-Lagrange points, including the two endpoints, let's say assume they are between small m and capital M. Then all these guys are between small m and capital M. Then theorem here, right, for first order scheme, as long as my omega lambda is less than or equal to minimum of omega 0 and omega k of lambda 0. Omega 0 equal to omega k because these Gauss-Labato rules are symmetric. So as long as I have a more restrictive CFL condition, so to take care of this, then this guy, this H acting on them is between small m and capital M. That's my first order sentence. This is also between small m and capital M. Every one of this is between small m and capital M. And the coefficients are all positive, they sum to 1. So the right-hand side is a convex combination of a bunch of numbers, all of them being between small m and capital M. Hence the result is between small m and capital M. So this is the only condition besides this condition, right? So all you need to assume is that your polynomial, when evaluated at Gauss quadrature points, quadrature points are between the correct bounds. Then, with this CFL condition, you can mathematically guarantee that the next cell average is between small m and capital M. That's half towards your goal, right? Not quite there yet, only the cell average. Now, what do you do to close the gap? Am I okay here?
Lambda k, lambda by lambda wk. Only for lambda not in w.
He wants to say for WK.
Yeah, W0 equals to WK because of the symmetry. So the Gauss-Labato rules are symmetric. Yeah. So what I can claim is that if somehow I can manage to get my solution at time level n to be between small m and capital M for the Gauss-Labato points, then I can guarantee that my scheme computing the next cell average will not go out. Hence, it will be accurate. Right? It will not go out. I have not applied any limiter here. So it's an accurate cell average. Does not go out. Now the question is, of course, cell average doesn't go out, but the polynomial could go out at the point. So I still need the limiter. Of course, I need the limiter. Wouldn't work. So now what would be the limiter? The limiter is very, very simple. It's this limiter. So you have a polynomial. You don't touch the cell average. So you have a polynomial px. You don't touch the cell average. Let me call it, px. You don't touch the cell average. So you subtract the cell average. This is for time level n plus 1, but I already have the cell average being okay. Polynomial, I subtract cell average, I add it back. So this is, if I don't do anything else, this is the px. I just multiply the theta. So this is my modified px. So my limiter is here to compute this theta. Now, what do I do in this theta? Well, I evaluate at these points, and then I take the minimum, I take theta to be the minimum of 1. Now, I don't remember the formula. Let me think. Did I bring the formula? Unfortunately, it's not in your notes because it's newer than that. I can work out the formula maybe, right? So the idea is that if you have the mj, which is the minimum of p of xjl, L between 1 and k, so you compute the minimum of these 4 guys. You also compute the maximum of these 4 guys. Then you can compute this theta. This theta, of course, is theta j. If theta is a different number or different cells. The theta j would be let's see. If this is mj, and I have to bring it to m, then I should multiply this by m over mj, right? No, mj over m. mj minus u8j m minus u8j. Let me see who is bigger. In this picture, mj minus u8j is bigger. The bigger thing should go to the bottom. I think it is this. u8j minus m, u8j minus mj. So let's see if I'm correct, right? So if mj is bigger than m, then you are subtracting u8j minus mj is a smaller number than this. Then this ratio is bigger than 1, then you take 1. Yeah, I think it is something like that. But I can be wrong. I can be wrong. So you read this picture to see, basically you want to bring this point to this end. So that theta is doing that. You modify this polynomial so that if the polynomial, the cell average is already above m, but the point can be below. If the point is below, you want to scale the difference between the polynomial and the cell average so that it goes to this level. So you can compute the theta. It's algebra. So I think this is correct. And the other one is symmetric. So the other one would be the bigger one is on bottom. So mj minus u8j at the bottom, m minus u8j. How about that? I may be wrong. But you get an idea. So this formula is extremely easy. You only compute your polynomial at the predetermined quadrature points. Predetermined quadrature points, you compute there are 4 or 5 of them. You take the minimum of the 4 numbers, maximum of these 4 numbers. You put in here, you get theta. And you put theta here, you get your modified polynomial. That's the limiter. So it's even simpler than min-mod. Purely local. Does not talk to neighbors. So the limiter is completely, you give me the polynomial, I just perform this operator locally. Now, after this limiter, then this assumption will be correct at time level n plus 1 again, because that's how the limiter is defined. Right? It brings every quadrature point up to the bounds.
But in between, it can
in between can do anything.
So it can go out of the bound.
Can go out of the bounds. So later I will state exactly the same.
That's right.
Proofs. Is it correct? Okay. No. Okay. Now I'm all set. The only question, I'm not all set. The only question is, you do this limiter, right? Does this limiter kill accuracy? You know that the TVD limiter kills accuracy. So does this limiter kill accuracy? If it does kill accuracy, then it's no good. It's as good as a amount. Right? Hypothetically, it could kill accuracy because the theta could be less than 1. Could pick any one of these that could kill accuracy. Right? So you have to prove that this limiter does not kill accuracy. You may not believe me, right? You might think, oh, it must kill accuracy. Okay, not kill accuracy. But there is a lemma which I don't want to prove anymore, but the proof is a few lines. It's a very beautiful proof that this limiter does not kill accuracy. Well, of course, this is not the right statement. The right statement would be that. The right statement would be, suppose the cell average is computed up to order h to the k, right? Suppose the unlimited polynomial p x is accurate of order k, then the limited polynomial p mod x is also accurate of order h to the k. The concept can be different. Okay. This lemma at the beginning beginning, we prove it case by case. So piecewise linear, piecewise quadratic, piecewise cubic. But later we find out that you just use a simple fact of norm equivalence. So finite dimensional space, all the norms are equivalent. Essentially, you use a similar fact like that. You just prove it for all k. And this is verified in the molecular also. So this limiter is a very, very mild limiter. It does not kill accuracy. Let me explain to you why intuitively it does not kill accuracy. Look at this picture. The cell average is above the bound. The true solution, if it exists, is also above the bound. That's the key. The true solution, the exact solution for PE is above the bound. It's not below here. Your numerical solution is below, that means you are in error. So you are putting it up to this, you are getting closer to the exact solution. Roughly speaking. Well, that's not proof because this point is closer to the exact solution, but how about the other points? Because you use a single number to scale every point. But roughly speaking, this is the reason that you can convince people this is a very mild limiter. It does not really kill accuracy. But this is a mathematical fact. So here, mathematical fact. So the final theorem is that if you apply this limiter, then exactly here. So if at time level n, we have P of xjl between m and m, then at time level n plus 1, so let's say this is star also holds. How about that? That's the theorem. So it's modifying from my wish list a little bit. Let me tell you what the wish list can be done also. The wish list is to say if this polynomial at every point is between small m and capital M, time level n, then it is true at time level n plus 1. It can be done. It's the same trick. However, the cost is tremendously bigger because for that, you would have to find the minimum of a polynomial. You might say, well, no big deal. Polynomial, take the derivative, set it to 0. That's the candidate points for minimum. So, and I know the root formula for polynomials up to degree 4. So that means I can handle polynomial of degree 5. That means I can handle P5 dt, 6 order dt. I can find the 0 exactly, find the maximum, minimum exactly. It's true in 1D, not in multi-D. Right? But this trick, because it uses only quadrature rules, it's trivially extended to triangles to multi-D. Because all you require would be a quadrature rule such that the integral of a polynomial on your triangle equals to the sum of the point values at these quadrature points with positive weights. This you open the finite element book or open the book, you find such quadratures. You don't even need the optimal one. Right? The optimal one is good for proof to get this omega 0 as big as possible, the CFL number, but you just find any one, at least you have Maxwell principle satisfied T. So the biggest advantage of this trick is that it works to polynomials of any degree on any triangulation, on any abstraction dimension. Yeah, because it uses really very little time. It uses you see the only non-trivial thing is that the quadrature rule. Other things are trivial, right? So it's I really like this. So I'm selling this thing everywhere.
Is the time step very small?
Yes, it's 1/6, 1/4, things like that. So depending on what kind of quadrature rule you have, let's say 1/6. But let's say if it's 1/6, it goes all the way to P3. It's P3. The regular DG also has 1/7. Yeah, P2 has 1/5. So for DG, it's not a big deal. For finite volume, it is a problem. For finite volume, because people go all the way to CFL 0.8, then this is a rather severe restriction. However, this is how we actually implemented this thing. You don't have to do this if your solution is already between the two bounds. So you post-check, you use your usual big CFL compute. Then you check the next time level. If every Gauss point is in the bound, you continue. If they are not in the bound, you come back, you reduce your time step and recompute. So our experience is that in the long time history, only a few time steps that this is crucial. So, so you don't, yeah. So this is nice theoretically, but in practice, there are tricks. So the good news is that you know that when you come back and take this small time step, you don't have to worry unless you made a coding mistake. Otherwise, the cell average will not go out. Right? So it's very difficult to achieve. You think about it. A lot of other things, they don't guarantee this time level you can do anything. How do you guarantee the next time level the cell average doesn't go out? If it goes out, that's the end of you because you cannot touch cell averages. If the cell average goes out, you are done. You are killed. If the cell average is in, you can limit to get other guys in. Right? The cell average is out. There's no way you can limit. So this is a very nice limiter that I would want to explain to you. So unfortunately, today I spent totally on hyperbolic. So we would have to postpone the parabolic thing to tomorrow. Sorry about that. But I think it's okay because the hyperbolic thing is the backbone of DG. So DG performed the best for hyperbolic. So it's good to spend a bit more time on it. Tomorrow I will try to tell you how to do higher order derivatives for parabolic and hopefully a little bit, maybe 30 minutes of KDV. So I will not go into such details tomorrow. So it will be more sketchy.